Welcome back to Calculus 1. In this lecture, we're going to introduce one of the most important results in calculus and all of mathematics with something known as the Fundamental Theorem of Calculus. Okay, now this is called the Fundamental Theorem of Calculus because there's a fundamental relationship between what we've been saying are these two different parts of calculus, differential calculus, and most recently, integral calculus. Each of those parts of calculus has a fundamental quantity, either the derivative or now definite integral, and there's a relationship, as we'll see, between the process of finding derivatives, differentiation, and the process of finding integrals, definite integrals, with what we call integration. All right, now if you think back to where we were recently, we started introducing the problem of finding area by thinking of finding the area beneath a graph over the x-axis. We had to modify that to deal with the case of the graph going below the x-axis. So we introduced the idea of net signed area, and we can answer this question: find the area between the graph of the function and the x-axis over the interval. We introduced that most recently as net signed area, allowing for area between that graph and the x-axis to be both above and below the x-axis. All right, and we were trying to evaluate a definite integral. That's how we'll calculate and answer this question. And there were two ways that we approached it. The first way, conceptually in the course, was that we started trying to find an approximate area by using rectangles, or an approximation with rectangles. The second way, most recently, when we introduced the definite integral, if the function is simple enough that its graph can be represented as corresponding to simple geometric shapes, we can use simple area formulas to get the area that way. Now, there's some problems with those two approaches. The first way here, it's not exact. It's only an approximation. You can make it as good as you want by using more and more rectangles, but still, it's not exact. The second problem is that, well, what if the shape is not a simple geometric object? We may not have an area formula for that, so we might want something a little bit different than trying to just look at it as a region represented by a bunch of triangles and rectangles. All right, so the two approaches here are a little bit limited. And if we think back to an example that we did when we went through doing approximations, very simple graph of x squared, your basic parabola. Let's say we were to find the area beneath the graph of x squared over the interval 0 to 4. Now, we don't have any current exact ways to answer this. We can do an approximation and make it as good as we want, but again, that's still not exact. So as it turns out, as I'm alluding to here, is there a simple way to answer this question, to find that area? As it turns out, there is, which is what we're going to learn about in the first version of the Fundamental Theorem of Calculus. There are two versions. We'll address each version in a separate part for this lecture. So let's get to the first version. The first version for the Fundamental Theorem of Calculus says something about evaluating definite integrals. Okay, so there's a lot of different ways to label these two different parts. Some textbooks call them part 1 and part 2. Those parts don't tell you what the versions are referring to. So this version for the Fundamental Theorem of Calculus gives us a way to evaluate definite integrals. All right, and basically what it says is we have a function, little f, that's continuous on an interval, and capital F is any antiderivative for little f. Then what we get is a very simple way to evaluate the definite integral of little f. If you take a look at the bottom there, it has the definite integral of little f from a to b, and that equals capital F of b minus capital F of a. Now, the names of the functions don't matter, but the relationship does. Little f is the function, capital F is one of its antiderivatives. So what the Fundamental Theorem of Calculus says is we can evaluate a definite integral by plugging the endpoints a and b into an antiderivative for our function. Sounds rather simple, but this is the fundamental relationship between definite integrals on the left and antiderivatives on the right there. Antiderivatives were a differential calculus concept, and this fundamental theorem links them together. It's arguably one of the crowning intellectual achievements for all of humanity, hence why it's called the Fundamental Theorem of Calculus. All right, now this is a kind of a useful result in the calc sequence and leading to what comes next. There's a few remarks I want to make. The first is basically that any antiderivative will work. Now let's think back to a concrete example. Let's say we have our function, little f, as x squared. Now, when we introduced antiderivatives earlier in the course, we mentioned, well, basically if there's one antiderivative, like 1/3 x cubed, then you can add any constant, and that gives you another antiderivative. So instead of saying this function f has a single antiderivative, there's technically an infinite amount of them. Since there's an infinite amount of different constants we can plug in there. We could have c equals 1, c equals 2, c could be any real number, and that would give you a different antiderivative. So we can use any of those antiderivatives to implement the fundamental theorem of calculus. We'll look at that in detail in an example in a moment. The second remark is more or less just on notation that's standard through the calculus sequence. And it's dealing with that right-hand side, f of b minus f of a, f being the antiderivative, capital F. Well, usually we just write that difference, f of b minus f of a, with what's called an evaluation bar. So if you take a look at that expression, capital F of x and then the vertical bar with a and b, that just means plug in b and a individually and subtract. So we evaluate the antiderivative at the endpoints. Now with that notation, we can rewrite the fundamental theorem of calculus for this version in that bottom line down there with the evaluation bar. Make sure you're comfortable with the notation. You'll see that scattered throughout questions that we'll answer in this lecture and in the homework questions as well. All right, so let's go ahead and answer that introductory problem. How do we find the area beneath the graph of x squared over the interval 0 to 4? An approximation would take us minutes. Applying the fundamental theorem of calculus, this version will take seconds. So let's get to example 1, which is evaluating this definite integral. All right, graphically, we can interpret that as the area beneath that graph over the interval 0 to 4. X squared remains entirely above the x-axis, so we can interpret it as regular area instead of net signed area. And if you think back to when we did the basic introduction to integrals by approximating area, we did a calculation using the midpoints of 4 rectangles, and we found that we got an approximation value, the midpoint approximation, as 21. So we saw that was a very accurate approximation. We did give the exact answer earlier, 64/3, which is about 21.33, and this is very close as an approximation, but still not exact. All right, that midpoint approximation took us maybe several minutes. Well, let's point out how in seconds, the fundamental theorem of calculus will give us the answer here for that exact area. All right, so we apply the fundamental theorem of calculus, the FTC, which is our abbreviation, by looking first for an antiderivative for the function that we are integrating, the function inside the integral, which is x squared. That's really simple. We did that earlier when we introduced antiderivatives. 1/3 x cubed differentiates to x squared. We could use any antiderivative, however. We're going to use the simplest one to answer this question. And if we apply the fundamental theorem to evaluate this definite integral, we plug in to the antiderivative the endpoints 0 and 4. So plug in 4 and then subtract when you plug in 0 to that antiderivative, capital F of x equals 1/3 x cubed. All right, and again, that goes really quick. Aside from adjusting to what the FTC tells you, the antiderivative, very simple to find using the power rule for antiderivatives. And then we just plug in the endpoints of our interval, 0 to 4, and we get the answer here, 64/3. The exact answer comes to us much, much faster than any approximation. That's kind of interesting that the exact answer comes faster than the approximation. Okay, so that's basically it. Before we move on, I want to take a look at a follow-up. We're emphasizing in the middle of the page there that any antiderivative will work. So let's repeat kind of this problem using a different antiderivative. It's not very different. There's just a different plus c. So let's say we use as our antiderivative of x squared 1/3 x cubed plus 1. That still differentiates to x squared. Let's see what difference, or maybe no difference, this antiderivative makes in evaluating the definite integral. All right, we use this new antiderivative, 1/3 x cubed plus 1. Now, when we plug in those endpoints, 4 and 0, and subtract, well, notice the plus 1 there, that just subtracts out. If you are careful and use parentheses when plugging in those endpoints to the antiderivative, you have the plus 1, but then in parentheses minus plus 1. 1 minus 1 just cancels out to 0. So we still get the same answer, 64/3. The specific antiderivative that we use doesn't matter. So usually we go with the simplest antiderivative, which we'll address in a remark following this. Okay, now again, hopefully you see how quick this goes. Applying the fundamental theorem of calculus, this version, hinges upon us being able to find an antiderivative. All right, before we move on, let's just emphasize what we were looking at the end of example 1 with using different antiderivatives, just to kind of make the calculations easy in practice, since the specific antiderivative didn't matter. For instance, it didn't matter that we put the plus 1 in the calculation using that second antiderivative. We're usually just going to neglect it and have that plus c equal 0, since it subtracts out anyway. So you can see here, you can include the plus c in your antiderivative, but it will always subtract out. So we're just going to advocate to just take it to be 0 to begin with. That way you're not left with any more difficult or cumbersome expressions. We'll just stick with adopting plus c when using definite integrals with the fundamental theorem of calculus. The plus c will be 0. All right, let's go ahead and take a look at some other examples. There's really not much to this currently, since we don't really have many tools to find antiderivatives. So here's example 2, 3 parts. Pause the video and give them an attempt. We'll check in a few minutes. For each of them, almost most of the work, all of it, is in finding an antiderivative. We'll check in a few minutes. All right, welcome back. Some of these are simpler than others here through the various parts. For part A, the antiderivative is very straightforward, just some different functions, or basic functions, I should say. So here our function f of x, little f, is e to the x plus 1. We can just find an antiderivative term by term. So an antiderivative for e to the x is itself, an antiderivative for 1 is x. So with pretty minimal effort, provided you're comfortable with antiderivatives, as we covered earlier in the course. We get our antiderivative here, capital F of x, rather quickly. Always check in case you're not sure. Take your antiderivative, capital F of x, differentiate it, and see if you get your function, little f of x. And here, you'll find it works out. All right, hopefully that went really quick. The last part, to use the fundamental theorem of calculus, we would take our antiderivative, e to the x plus x. From our previous comment, we're going to take the plus c, the integration constant, to be 0, because it doesn't matter, it subtracts out. And to that antiderivative, we'll just plug in x equals 2, and then subtract when we plug in x equals 0. And if you're careful using parentheses, plugging in 2, you'll get e squared plus 2. Plug in 0, you'll get e to the 0 plus 0. E to the 0 is 1. And if you subtract those values, 2 minus 1 will give you that plus 1 at the end. And we are left with e squared plus 1 as the answer to this definite integral. All right, now before we move on to part B, I always think it's good where possible to kind of visualize, understand concepts in multiple ways. Here's a calculation using the fundamental theorem of calculus. But let's visualize this, interpreting it as the area beneath the graph of e to the x plus 1. We have the area there, exact area, e squared plus 1, and let's just visualize that. So think back to maybe your pre-calc course. The plus 1 on the function shifts the graph up 1 unit. The asymptote moves up from y equals 0 to y equals 1. And since our definite integral is looking at the interval from 0 to 2, we just look at basically the area beneath that graph over the interval 0 to 2. All right, and well, we actually calculated that exact area. That red shaded area has area e squared plus 1. All right, let's go through part B. This one's a little more complicated. There's a common error that I usually see when finding the antiderivative. And think first how differentiation works. Since we're multiplying, we wouldn't differentiate each individual factor. For the same reason, we don't find an antiderivative individually for each factor. The common answer, wrong answer I get for the antiderivative is right here. What you would get by finding the antiderivative for each part individually in parentheses and then multiplying. All right, now how do we find the correct antiderivative? Well, what we mentioned earlier with antiderivatives, rewrite the function before looking for an antiderivative. There's really not much we can do with that function. It's written with 2 factors, so you can expand or FOIL it. And now we can find an antiderivative term by term. Now it's a sum of powers of x. All right, and if you do that, apply the power rule. We're going to apply that to each term. You should get as your antiderivative 2/3 x cubed plus 5/2 x squared plus 2x. That's most of the work for the question, at least calculus level. And all we have to do to that antiderivative is plug in x equals 3 and then subtract once we plug in x equals 1. Now this one is going to get a little tedious due to the fractions 2/3 and 5/2, but that's not calculus concepts. That's just basic arithmetic concepts. All right, if you plug in 3 and you bother to fiddle around with common denominators, you can write that result when you plug in x equals 3 to the antiderivative as 93 over 2. When you plug in x equals 1, you can write that antiderivative value as 31 over 6. And then if you subtract, again, using a common denominator, you get the exact value, 124 divided by 3. And just to get an approximate answer, just to satisfy maybe application problems in science and engineering, this definite integral comes out approximately to 41.33. The exact value, however, is 124 divided by 3. All right, let's move on to the last example, part C. This was one that we addressed earlier when we introduced the definite integral and the idea of net signed area. At the time, we said we couldn't find the area beneath the graph of sine x over the interval from 0 to pi. Well, now with the fundamental theorem of calculus, we can, and it goes rather quickly. The calculus goes really quick. It's probably the evaluation of here, the antiderivative cosine, evaluating basically from using the unit circle. We'll go through that. So our function here is sine of x. The antiderivative, rather simple, negative cosine of x. Definitely check that by calculating the derivative of negative cosine of x. There'll be an extra negative that cancels out, giving you your function, little f, as sine of x, so the signs work out. We have our antiderivative, and all we have to plug in now to that antiderivative are x equals pi, and then subtract once we plug in x equals 0. Now, I always found students in calculus sometimes forget the fundamentals. Pre-calculus might have been a while ago, more than a semester ago. So let's just briefly review those values in case they're not kind of readily at the forefront of your mind and familiar. Just think of a basic unit circle. We're looking at the angles as radians. So cosine of 0, that's corresponding to cosine of the angle 0 radians. All right, and cosine of 0, we can take a look at the x-coordinate for the point on the unit circle. The x-coordinate is positive 1, so cosine of 0 is 1. When we go a half rotation, kind of in the positive rotational direction, counterclockwise, an angle of pi radians puts you right on the negative x-axis, and the coordinate that corresponds to that angle on the unit circle is negative 1, 0. What we can conclude from that is cosine of pi corresponds to that x-coordinate. Cosine of pi is negative 1. All right, now just be careful when you plug in those values. This is the part of evaluating the antiderivative. There was a negative that popped up in the antiderivative. The antiderivative was negative or minus cosine of x. So just be careful with your signs. Cosine of pi is itself negative 1, and there's a minus in front, so that cancels out, giving you 1. Then you have minus negative cosine of 0, which again cancels out to positive 1. So we get our exact area here, the exact value for the definite integral, as 2. This one can also be visualized. Here we have a decent sketch by hand for the graph of sine of x. And if we take a look at the area beneath that graph over the interval 0 to pi, that red shaded area comes out to be exactly 2 units for area. Two, whatever your favorite units for area would be, square feet, meters squared, whatever units you're using. Okay, so that pretty much deals with examples related to the first version, as we're going through it, for the fundamental theorem of calculus. The first version says something about a way to evaluate definite integrals. We evaluate definite integrals using the fundamental theorem of calculus by finding an antiderivative. In the second part, which follows this, we'll address the other version for the fundamental theorem of calculus, which thoroughly establishes the relationship between differentiation and integration.